In this clip, I will outline the basic differences between Bayesian and Frequentist inference. There will be no technical details, and I will explain it in a context of a regression analysis. So assume that you have some knowledge of regression analysis and what we want to achieve with it. And here we go. Here is our little very simple regression model, linear, one explanatory variable. Our error term, which let's assume it's normally distributed with mean 0 and some variance sigma squared, and let's call that model 1. This is our setup. Now when we do this, when we do a regression analysis and specify such a model, we have some parameters of interest in mind, and these are the alpha and the beta mainly, and perhaps also the error variance. Let's collect them all in a vector, alpha, beta and sigma squared. But now, for reasons of simplifying the slight graphical analysis that is going to come, let's just concentrate on these two, the alpha and beta. So these are the coefficients which perhaps describe the relationship between, let's say, wages on the left-hand side as the y variable and the years of schooling as the explanatory variable on the right-hand side, to just pick a very simple example. Right, so let's concentrate on the alpha and beta as the coefficients of interest. Now we'll juxtapose what frequentists and what Bayesians would do. Now firstly the setup, and that's very important. A frequentist would basically say, all right, I'm interested in that theta, and the theta is unknown, but it is fixed. There's one true value for the alpha, the beta and the sigma squared. A Bayesian, however, would say that theta is a random variable. So it doesn't make sense to only talk about one true fixed value of theta. There are many values of theta that would be possible. Now, what do we want? A frequentist basically wants one estimate of theta, theta hat, something he or she would call the best estimate, however best is defined, the best estimate of the unknown but fixed theta. Yeah, we are after one value, and that makes sense because we think there is really one true value. A Bayesian, however, is after a distribution. We'll call it a posterior distribution, a distribution for theta conditional on information contained in the data x and y. Right, so x and y, this is our data. We want a distribution of theta. What do we need? So what a frequentist needs is basically our model here, which we labeled as model 1 above, our linear relationship and a distributional assumption for the error term. So we need the model and we need data x and y. A Bayesian would need exactly the same for starters. So it needs a model that relates y and x with a distributional assumption, and we need data. But on top of that, a Bayesian will also need what's called a prior distribution of theta. So that's a distribution of theta, but without being informed by the data x and y. So how we do it? So how do we get what we want? What would a frequentist do? Now that sort of depends what estimation method you use. If you do a course in econometrics, you would know some different ones. For instance, OLS, you get beta hat by just calculating the covariance between y and x and divided by the variance, and the best value for alpha hat you get using this little formula. And if you need to use maximum likelihood, again in this clip I'm not going to explain what that is, you either know it or you don't. We find one possible theta, or the best theta, and it's the best theta is the one that maximizes a likelihood function. Right. So, but we get one value. We use the one which maximizes the likelihood function. What does a Bayesian do? Now, a Bayesian, really everything builds on this little relationship. The posterior distribution, this is what we are after, is proportional, and that's what this little sign means, is proportional to the product of two things. Firstly, the likelihood function. Okay, so that's actually the same function which we just referred to when discussing what a frequentist would do. The second element is the prior distribution of theta. Now, this is a distribution. Now, remember, we're concentrating on alpha and beta only, so we're thinking of two variables. So a prior distribution that looks perhaps something like this, okay, a multivariate distribution. So that likelihood function, we can calculate that for each value of alpha and beta. Okay? So in a way, that's a three-dimensional construct as well. For each value of alpha and beta, we can calculate that value. And then we multiply these two things together, and what you get then is what's called the posterior distribution, and that's a distribution again. So here it's worth reflecting for a moment. So the result of a Bayesian analysis is a distribution, and this distribution will tell us which combinations of alpha and beta we find most credible. A frequentist, however, calculated just particular values for alpha and beta, or as they are collected in theta. So that's very, very different. How would we perform inference? A frequentist would do, for instance, something which is called hypothesis testing. We postulate a hypothesis, for instance, beta is equal to 0.5, and an alternative that beta is larger than 0.5, and then we calculate something which is called a p-value, which is really a quite strange construct. It is the probability that beta would be larger than 0.5 if the null hypothesis was true, and that's very important. A probability if h0 was true. Now, wouldn't we much rather just have something like what's the probability that beta is larger than 0.5 without having to make an assumption about a particular hypothesis? Now, a Bayesian can read such a probability straight from the posterior distribution. That's very convenient. That's extremely convenient. And it sort of makes more sense. However, this sort of more sense in terms of inference comes at a price. This price is sort of twofold. Firstly, these calculations here, which I sort of graphically try to outline, they're not always easy. We get more and more software packages that help us with these, but often we need a lot of computational power to do these calculations. And secondly, we need as an input this prior distribution. Now, it can be a strength or weakness of the method, but we have to think carefully where it comes from, and different people may want to use different priors, leading to different results. Now, all of these differences really originated from this different assumption at the beginning. A frequentist assuming that theta is unknown but fixed, and a Bayesian assuming that the theta is unknown but is really a random variable.